right. So I want to share. All right. So does everybody see that?
Yes.
Yeah.
All right, good. Okay, so here's quiz number 2. This is one of my favorite little exercise for linear regression and correlation. So what we had to do with this particular data set is get the x-axis and the x values and get the y values situated correctly, okay? And I underline the question so that we kind of know what is going on. So first thing we wanted to do is sort of think about the correlation coefficient, right? So the correlation coefficient has a negative sign. It has a relatively strong correlation, and it is a linear correlation. So those things right there are sort of what we're trying to get out of the correlation coefficient: the strength, the direction, and the linearity. And so it's easy to slip into sort of the next question. The next question is the square of the correlation, or the coefficient of determination. And all we have to really do here is take this value, the R value, square it, and we would get a value that is not negative, it's positive now, and we can start to think about this value as the R squared value. And what this indicates is that the variation of Y, 75% of the variation in Y, or the variation in the length of employment, is attributable to the number of work days absent, all right? So that is a relatively nice statement. 75% of the variation in length of employment is attributable to your absence, okay, or your obligation to get to the job. All right. C is which one is the response variable, which one is the explanatory variable, and this is pretty straightforward. The number of work days absent, that's the X value, and then the length of the employment is the Y value. All right. Questions so far? All right. So if we got our calculators out, we put these values into the calculator, and we had to be very, very careful about assigning the x-axis and the y-axis to the right variable. All right, so this question here, C, gets us there. And once we have that that figured out, we can start to think about the linear regression line that might come out of this. So the slope is negative 1.08, Note that the negative sign is like the of the slope is very consistent with the correlation coefficient that is -2. The y-intercept is 9.44. Put that together in terms of a linear regression equation, and we would have the length of employment is equal to the the number of work days present times the slope, and then we add on the y-intercept. Okay, and so this last question on page 1 is now we're going to be predicting what the length of employment is associated with an employee that's been there or has 5 work days absent, and that prediction is 4.0 years. Everybody got that?
Yeah. Yep.
All right, pretty straightforward. Now this one too I like, although we're not going to be seeing much baseball, except they're talking about baseball in Arizona. I don't know how that's going to work, but anyway, here we go. We start with a linear regression equation, and that is given to us. Okay, time is equal to 158, that is minutes, and this is the slope, 2.53, and the number of runs that go along with the game. So a pretty interesting little distribution of values, but we're going to use these along the way. So first we want to use the equation to find out, predict what the time length will be if there were 5 runs scored. So all we have to do is put 5 into X and start to think about what that value is, and that's 171 minutes, all right? So this is the way I would have sort of said it. The length of a game is predicted at least 161 minutes when 5 runs are scored. All right, so that here is where 5 is, and we'll probably go up to this value right up here. Right here is going to be part of a residual. All right. So the next B is finding the residual, the observed minus the predicted. We are using this point as the observed, and we're using this here as the predicted. And we're just using subtraction to get a value of 18.35. And we're talking about this dot right here, this point right here. All right. Now we slip into the idea of influential observations and outliers, and we were thinking along the lines of this point here, 18 being the x-axis, the x value, and 210 being the y value. We're coming out here, and it's about 18. This one here would be the influential observation. All right. And the reason why it's the influential observation is because we're going across the x-axis, and this value here represents a value that is really very stretched out across the horizontal axis. Likewise, we're talking about outliers, and outliers are a little bit different as defined by the book. We're going to be using the point 10 as the x value, 235 as the y value, and that one is, that is this point right here, okay, all the way up here, 10 right here, and 235. That's my call. And this would be sort of an outlier. And why is that? Why is that the outlier?
Because points with large residuals are usually outliers.
Okay, so we're really sort of looking at this and saying, boy, that number here has a huge, right, residual, right? So in many ways, what we're doing is we're looking at the residual and saying, wow, that has got to be some kind of error or something like that. And it is sort of on the y-axis. So the influential observation is on the x-axis, and the outliers are determined by the distance of the residual for the y direction.
Also for C and D, if you were kind of around the same points as you, like within like 1 to 2, like I had 11, 235 for D, would that be fine?
Oh, absolutely. Okay. My eye is as good as your eye, you know, and you know, and I'm wearing glasses, and I might have got that one without my glasses on. So, yep, there's no worries there. Okay, so this is another reason why I like this idea. You can really actually see what is going on when you're putting this together. So if we have a linear regression line and the slope is 2.53, what are the units there?
Runs.
Okay, 2.53, all right? So let's go back up here, right? Under A. Here is the slope, right? 2.53, all right? That is in minutes, right? So one run scored adds 2.53 to the game with a intercept of 158. So I tried to use my best composition. If one run is scored in the game, the time the game lasts is predicted to go up by 2.53 minutes. All right, and lastly, interpret the intercept. Now, in some cases, we don't ever use the intercept for anything meaningful, but in this case, it is somewhat meaningful. And so you can see maybe no runs scoring through 9 innings. That is, nobody has scored yet. And we would predict, what would we predict the time would be in a game like that?
158 minutes.
You've got it, 158 minutes. Okay, so that's the quiz. And again, I was very happy with the scores, and I think you'll be happy too. Questions? All right, so let me go and I'm going to get the back end of chapter 7. All right.
Are you going to be posting the Chapter 7 PowerPoints?
Yes, I will.
Okay.
Sometimes, Bruni, I am working on the PowerPoints right up till class time. And so today I will put it up and let you get to it.
Gotcha. Thank you.
You're welcome. Okay. Now, the last time we met, I don't want to be too redundant here, but we were thinking about normal distributions. Okay, normal distributions are very, very important. And we always want to sort of get into a position where we have sort of a symmetrical, bell-shaped sort of curve. If we have that, then a lot of things go our way in terms of using statistical tools. And if we call it a normal distribution, we don't really think about the shape too much after that. We don't have to worry about giving us a parameter that tells us that it's a normal distribution. All we need is a center and the spread. That is, we need the population mean and the population standard deviation, the mean being mu and the sigma being the standard deviation of the population. And we're going to run our probabilities, thinking that the area under the curve is equal to 1. That's the highest probability value can be. We want to segment the area under the curve and use different segments to ask questions about the data. All right. So as sigma increases, the curve flattens. All right. And as sigma decreases, then the curve becomes much more narrow and values that are very close to the center. And we've got this under our belts too. Now, I went back to chapter 4, and we did do some work with this, and it might be a little redundant, but on the other hand, we might want to revisit it so that we can apply the area under the curve as something as a probability. Okay, and I'll get into this in a little bit. All right. So here we have a bell-shaped curve. This is obviously a normal distribution. All right, it's symmetrical, and it has a mean. This distribution has a mean that is 100. All right, we have a standard deviation that is 10. And if you see sigma and if you see mu, then you know that this is a distribution that is a population distribution, right? So we're working with a population here. Now, I would like to emphasize something that goes along with this. And what we're seeing is sigma equals 10, okay, from 100 to 90, that is 1 SD. Everybody sort of see that? Boy, I can't really use this very well. All right, I know. I'm not an artiste. Okay, so if we went down and we started to think about 80, that would be 2 standard deviations. Everybody sort of see that?
Yeah.
Okay, so how about we get into 70? What are we starting to see? If we get through to 70, which is down here, right? That is 3 standard deviations away from the mean. All right, so the values down here in this tail, right around there, are they frequent or are they rare?
Rare.
They're very rare. They're very rare given that the center is 100 and the standard deviation is 10. So these become very rare values. Now they might be wrong. They might be error. It could be something that is very, very important though. It may be a very big find if we were to see something like that. All right, so we're going to sort of start thinking about what is inside. Hold on. Sorry. We're going to start thinking about what is inside of two standard deviations away from the mean. Now, what is the area under the curve between 80 and 120? What is the area under the curve? Well, we reach back. Do you remember the empirical rule? Or the 68, 95, 99.7 rule. So in this particular case, between 2 standard deviations away from the mean, okay, is going to be 95%. Everybody sort of see that?
Mm-hmm.
All right, and outside of those boundaries, we're going to have 0.05 or 5%, and we're going to divide that 5% and put them on what is called the tails, okay, right around here. Questions? All right. Now, we can take any one of these normal distributions once we've declared that it's a normal distribution with a certain center and a certain spread, then we can standardize that, distribution, all right? And we're going to be using z-scores. So we're thinking about a standard normal curve, and the standard curve is always, the mean is 0, and the standard deviation is 1. That defines a standard normal distribution. So here is a very same bell-shaped curve, and we're looking at right about here is 2 standard deviations away from the mean. Right about here is another 2 standard deviations away from the mean. And again, this is 95%. All right. So the book tells, sort of gets involved with these Z notation. I am not going to be using it much. It is very important in terms of describing probability, but for me, I look at it a little bit differently. So the Z-scores go from negative 3.89 to positive 3.89. And that is sort of the limits where almost all the observations are contained within those Z values of 3.9, negative and positive. So we did think of going to the table. We always had a standard Z table carrying it around. So let's just start thinking about these as probabilities. All right. So here is a value, and the Z-score is negative 1.62. What is the probability of lesser than negative 0.62? Well, we would go to the Z-score. We're looking at a table that has rows and columns. And this is part of the Z-score or the Z table that we're thinking about. So here is negative 1.6, negative 1.6 on the column, and then we go over the row, and it's 1.6, negative 1.62, and we're thinking about this value right here. This is the value that we're looking for. And that is then going to be the probability that is underneath this blue shaded part of the standard normal distribution. Questions about this? All right. Same thing here. Now, as we cross over from -3 all the way to +3, the area under the curve, the shaded area, is growing. And the Z-score for this is going to be 2.31. All right, that's right here. Now, what's the probability of 2.31? Lesser than 2.31. Okay, it's a lot larger than the last one. It's probably in the 90s. But we're doing the same sort of thing here. 2.31 all the way over to 1. We're looking at this value right here for our probability, 0.9896. All right, and that is the probability of that. Questions? And we want to, let's say, greater than 2.31. Now we're not concerned about this large area here, but the small area right in through here. Well, we know some of this, right? we actually know the area that's not shaded. We just figured that out. All right. So let's think about this. Greater than, Z is greater than 2.31. So now we're looking for an area under the curve. We would go back to what we want to see in this number right here. But we don't want that number. We want 1 minus that number. All right. So I'm going to take a breath here, and I'm going to ask you about what do you think this number right here is?
It's the area to the right of 2.31.
Okay, is that a very, very low probability?
Yeah.
It's really low, right? And what that means is the low probability means that this area right there is very unlikely. Does everybody sort of see that way?
Yeah.
All right. So that is a probability, and it's telling us that it's very, very unlikely. All right. All right, so what we're going to do here is a little bit different. All right. We want to see the smallest 2%. All right. That's what we want. 0.02. That's very small. That probability is very small. All right. So we go to our table. We look up the table, and we're thinking about the closest number that we can get to 0.02. This here is pretty close to that number, 0.02, and we want the z-score for that number. All right. So that is a negative 2.08. Questions about this? Likewise, we can do the same sort of thing, the largest 5%, and we're asking for a z-score with the probability of 0.05. Again, we go into the table, start to think about these values right here. It's probably something between this one and this one. All right. So we think the z-score is 1.64 or 1.65. That would give us a chance to get a third digit, and that z-score would be 1.645. Questions about this? We have been through this. I know that. All right, so we're thinking about probabilities and normal curves. All right, so x can be a random variable, all right, with a normal distribution of the mean u and the standard deviation sigma. And we can go ahead and get two different z-scores when we're thinking about segmenting one tail and another tail on the other side. So we might need 2 z-scores. All right, so let's take this example pretty quick. All right, so what we're thinking about is registration. All right, and we think that the mean of the population is 12 minutes during registration with a standard deviation of sigma equals 2 minutes. So we can start with a sort of let me go back here, see if I can't, not too bad, right? 12 right there. All right. So we have these values here, these parameters, and we want to randomly select a student that is less than 9 minutes through the complete registration. What are we going to do here? What are we going to do? Do you remember the z-score, the z equation? How about z is equal to x minus mu over sigma? Remember that? So we're going to take the value 9, put that in for x. We're going to put 12 in for mu, and sigma is going to be 2. So this gets us a z-score, and we can then go and try to think about what the probability of that is. And if we were to look for a value, a z-score of negative 1.5, this would be the probability of that value. So what is the probability that a student gets through lesser than 9 minutes? 0.067. All right, so let's do the same thing for 13. Now I would appreciate, understanding where 13 is. 13's right against 12. So it's not going to be an area of 50, but 50%, but it might be 60%. All right, so there's 13. And 1 is 0.5. One minus this value here, which is associated with the z-score right there. And we get this area to be 0.31. And of course, we can do other things. And if we needed to, between 7 and 8, between 7 and 15, we want 2 z-scores, one at 1.5, the other at negative 2.5, and that would get us this value right there. Questions? All right, so here is a sort of a little twist in the idea. So oftentimes the students don't take log off properly, okay? it was decided to select a time so that only 1% of the students will be automatically logged off. What time should the automatic log off be set? Excuse me. How do we work with this? All right, so here is 0.01, very unlikely. We want to get a z-score that goes along with that. The z-score would be associated with 0.99, and we get a z-score. Here is our z-score right there. And that is associated with this probability here. And now we're going to solve, not for the z-score, but we're going to be solving for x. All right. So there it is. There is our value, 16.66. What are the units there?
Minutes.
So the units are minutes, right? So would it be reasonable to shut the student off after 16.6 minutes if we knew that the mean was 12? That might be reasonable if we want to get more people on and through the registration. All right, so that's what I have for today. Questions?
No.
Okay, Bruni, you have a question?
Oh, no, I'm good.
All right, so we're all going to have a good Easter break. Okay.
Thank you, you too.
Yep. And we'll see you on Wednesday, a week from today, the 15th.
Sounds good.
All
Thank
right.
you.
Thank you.
Thank you.
Thank you. Have a good break.
Be safe.
Happy Easter.
You
Happy
too.
Easter.
break.
Yep.
Have a good Easter.
You got it.